All right, and with that, it is my pleasure to introduce our presenter for today, Carmen Chubasang. Carmen is a PhD candidate at UC Berkeley who's studying fire and forest. She's broadly interested in the causes and consequences of extreme wildfire and in the potential for woody biomass energy in playing a role for forest management. She has collaborated with the Energy and Resources Group at UC Berkeley on work related to woody biomass energy potential and is currently working with researchers at UC Davis on a decision support tool for sitting biomass energy facilities. All right, thanks so much for joining us today, Carmen. We're going to be switching screens here. Great, looks great. I'll let you take it away.
Hi, everybody. Thank you, Stacy, for the introduction. I will be doing about a 10-minute background on this web tool, how it was developed, the methods that were used, and then I will actually be walking you through the web tool, doing some demos about how it can be used, and then finally I'll take questions. And if we can't get to everyone's questions, or if you have more personal specific needs or technical difficulties, feel free to email me, and we'll also send out a survey with the survey that Stacy will be sending out that will allow you to express interest in some more small group help sessions and what your availability would be for that. So don't worry if you are having difficulties with the web map. There will be lots of opportunities for you to get my help. So a little bit of background on this project. It started out as a summer research exchange with a graduate student here at Cal who studies renewable energy. His name is Jose Daniel Lara. And since then, the project has expanded quite a bit. I'd like to give a shout out to the Data Sciences for the 21st Century program, which is an NSF traineeship that funded me to do that original summer research exchange with Jose. And then the Graduate Students and Extension Fellowship through UC A&R has allowed me to do outreach like this webinar right now. And Susie Coker, Jody Axelson, and Maggie Kelly are some of the folks at UC A&R who have helped me out with the web map. And then, of course, my advisors, John Bells and Scott Stevens, have been super helpful. And on this title page, you see Shane and Robert are folks at the UC A&R Informatics or NGIS program, also known as IGIS, and they helped build the web map. So I'll start out by giving a bit of a briefer on the tree mortality crisis. I'm sure many of you are very aware, but 129 million trees have been estimated to die since 2012, according to the Forest Service. And actually, just a couple days ago, they came out with the 2018 numbers, which show that an additional 18 million trees died. So this 129 million number is a little bit outdated. This is a state crisis. The governor, Jerry Brown, while he was still in office, declared a state of emergency because of this. How did we get here? Well, there are a few reasons why so many trees are dying. The underlying root cause that is predisposing a lot of trees to mortality is overcrowding due to over a century of fire suppression that is making trees more vulnerable to mortality and other stressors. But the more proximate cause that tipped a lot of trees over the edge was the drought we had in 2012 through 2015, and then insect outbreaks, in particular bark beetles, that fed off of that drought and caused a lot of the mortality. There is quite a bit of concern among state agencies and other groups about what repercussions might result from this widespread tree mortality. Just to name a few of the potential risks as a result of the standing dead trees, we're worried about hazard trees near important infrastructure that might fall and be a safety risk. We're also concerned about the potential for all the dead wood and fuel and debris that's been created by the dead trees to increase fire risk. So this graphic is from a paper by my advisor, Scott Stevens, and some others in 2017 that was discussing what we think based on our best expert knowledge of how fires behave, what fire risk might look like in areas that have been hit hard by mortality in the next couple decades. And this image is showing, an artistic rendition of how a forest that experienced high mortality might look in 10 to 20 years. You can see there's quite a bit of coarse woody debris and fallen trees on the ground. And then one other risk is the fact that these trees will release carbon over time as they fall and decay, not to mention the short-term bursts of carbon emissions during fire. So given all these potential risks, there has been quite a bit of interest in addressing tree mortality, but we are not well equipped with the best data available on where that tree mortality is and what it looks like. There is the potential to use more sophisticated methods to evaluate this, like satellite data, but right now what we're mostly relying on is aerial detection surveys, which are shown here. Aerial detection surveys look like this. There's a person in a plane flying over the forest, looking out the window at 1,500 feet altitude, and recording on a tablet where they see dead trees. They record polygons and list a number of dead trees that they see in there. These people are well trained, but it is not the, it's not the most useful data source in part because it doesn't contain any information on the actual biomass of the trees. It's just counts of trees. So you can't use that to tell how much biomass there is or even what percentage of the existing biomass has died. It's just a number of trees. What that aerial detection survey data looks like is this. This is a tree mortality viewer that's online. It's very useful. I encourage you to check it out. And it shows the polygons that have been detected by the aerial detection surveys. However, these data do not capture everything that we're looking for, as I said. So one way to make the data more useful is to combine them with forest structure maps. And the forest structure map that we used is from the Lemma Lab out of Oregon State University. It's called the GNN, or Gradient Nearest Neighbor Forest Structure Map. And this graphic shows how the process works to develop a GNN forest structure map. Basically, they combine plot inventories, so in this case, forest inventory and analysis data, or FIA, with spatial data from remote sensing and some other data sources. So they develop metrics that summarize each plot data location, as well as locations across a region that do not have plot data. They link the plot data with that spatial data in order to extrapolate or interpolate what areas that don't have plot data are most likely to look like. So they kind of plug in the plot data that they have into areas that don't have plot data based on how similar that area without plot data is to the area that has that plot data. It's a little bit confusing, but basically you can think about it as taking FIA data, which only has one plot per every 8,000 acres, I believe, and making that more useful by spreading it across an entire state based on what we know about every other area using spatial data. This example shows Western Washington GNN forest structure maps, but they also exist for California. And we used 2012 Lemma GNN maps. So they are a snapshot of what the forest looked like in 2012. We connected that GNN Lemma data with aerial detection surveys to overlay the polygons on top of the forest structure map. We calculated per tree biomass of dead trees based on the forest structure maps. And then we came up with biomass at fine spatial resolution. One valuable thing about this analysis is that it allowed us to overlay several years at once. So aerial detection survey has many polygons that were detected in different years, but not a really easy way to see for a given location how has the biomass changed across all years of the drought. So because we overlaid polygons on top of each other from several years, we can say cumulatively how much biomass died over the course of the last several years. And this is just an example from the Illilouette Valley in Yosemite to give you a sense of how that works cumulatively over a few years. So in the end, what we get is something that looks like this. On the left, aerial detection survey polygons, and on the right, biomass. It's at a finer spatial resolution because we linked it to the lemma data, which is on a 30 by 30 meter grid. Because there's some uncertainty about the aerial detection survey, we had to put a generous upper and lower bound on our estimates. So specifically, what there's uncertainty around is the size of tree that aerial detection surveys can detect. Some small trees might be hidden by the canopy and not detected, but for any given flight of the aerial detection surveys, we don't actually have data on what size tree can be seen. So to account for that, we perform the analysis 2 separate times. One is the upper bound estimate, which assumes that aerial detection surveys can detect all trees greater than 25 centimeters in diameter. And then we also have a lower bound estimate that assumes that aerial detection surveys can detect trees, all trees greater than 2.5 centimeters in diameter with equal likelihood. So that is a much more conservative estimate, the lower bound. And then when we show you live biomass in a minute, that corresponds to these same assumptions. So our live biomass estimates, for example, include all live trees greater than 25 centimeters when you're looking at the lower bound live biomass, because the live biomass lower bound corresponds to the dead biomass upper bound. That might make a little bit more sense when we're looking at the actual map. I just want to reiterate that the aerial detection survey data is imprecise, and the lemma GNN forest structure maps aren't perfect either. I do think that this is a useful tool, but keep in mind that it should not be used at very zoomed in spatial scales. So if you're looking at tree mortality around an individual building, for example, it's not going to provide the level of precision that you're looking for. ADS folks at the Forest Service recommend using it at a scale of 1 to 100,000 or smaller. Just keep in mind when you're using your best judgment of how to interpret these data that it is recorded by humans at 1,500 feet above ground. Before I move on to questions, I will show you the web map. First thing you do is go to this URL, which is in the webinar description, or you can just type it here based on what you see. If it does not work for you, if your screen does not look like this when you go to this website, check if you're on Internet Explorer, because the web map is not compatible with all versions of Internet Explorer. So if it doesn't look like this, try downloading Chrome or Firefox or a different internet browser. I am not going to show you this tutorial. This is just describing each element, but we can skip that because I'm describing each element out loud. This welcome screen just gives you a little bit of background on the project and my contact information so you can reach out if you have questions. And like I said, IGIS helped create the map. I will go through each of these little items up in the upper left, which perform different functions. First, zooming in and out. You can use these buttons, but I'm just going to scroll on my mouse. Next, we have the layer list. So by default, when you go to the website, the only layer that's showing is dead biomass upper bound estimates, which is why this box is checked, this little eyeball symbol. If I uncheck that, dead biomass will go away. I'm going to go through each of these map layers so that you understand what they each represent. I'll start out with high hazard zones. If you're not familiar with high hazard zones, they are a way that the state of California, in particular the Tree Mortality Task Force, is prioritizing areas of California for tree mortality mitigation and in particular tree removal. Tier 1 high hazard zones are only visible on this map when you zoom in because they are small polygons that just look like a mess when you zoom out. So in order to see them, check the Tier 1 high hazard zone box and then zoom into the map. These Tier 1 high hazard zones are specifically looking at highest risk areas because they're near infrastructure, they're near roads, buildings. That's why sometimes you see these very small kind of string-like polygons because they might be hugging a road, for example, or a creek. To zoom out, to actually see the tier 2 high hazard zones, you'll need to zoom out because they are much larger. They capture large areas that have generally been affected by mortality and also are important for humans. So they disappear when you zoom in more. Oop, gone, zoom out. There are the tier 2 high hazard zones. Next layer I'll show you is percent dead biomass lower bound. So this is a percentage of the dead biomass that existed in 2012, how much of that dead biomass was, or how much of the live biomass in 2012 was dead by 2017. It's a percentage of overall biomass that is dead. And then lower bound, like I said, makes that assumption that ADS can detect trees 2.5 centimeters or larger, whereas the upper bound dead biomass, you can see the densities are much higher of dead biomass, makes the assumption that ADS detects trees 25 centimeters or larger. Moving on, we'll look at dead biomass lower bound. The difference here is that it is quantities of dead biomass, not percentage loss. So down at the legend, you can see it's given in bone dry tons per acre or megagrams per hectare. And then dead biomass upper bound has higher densities. Next, we have live biomass. So like I said, live biomass lower bound corresponds to dead biomass upper bound. It's the other side of that coin. It's given in green, so you don't get confused with dead biomass. And then live biomass upper bound shows the flip side of the dead biomass lower bound. And one thing to note about these map layers are that they are semi-transparent. So if you want to look at dead biomass lower bound and live biomass upper bound at the same time, you can. The green pokes through from underneath that yellow. And then last thing I want to show is slope. So more red color means higher slopes. This can be useful for showing large areas that are more inaccessible because of steep slopes. And if you click anywhere on the map at any time, the values for that individual pixel will show up, including slope. Zoom to doesn't actually zoom in and out. It just centers the pixel that you clicked on. And then to leave, click an X. Great. So we've got our layer list figured out. I'll go back to the default. Next, I want to show you how you can toggle on and off the legend. I always leave it on, but if it's in your way, you can remove it. You can remove the layer list. And then this next button allows you to switch the base map. So here we have satellite imagery, and actually I'll take this off so you can see what that looks like by itself. And then this is more of like a Google Maps road map. Okay, now we will move on to selecting areas of interest to view subsets of the data. You can do this in 3 ways, either selecting a county, drawing a polygon, or uploading a shapefile. And I'll go through each of these 3 methods right now, starting with selecting a county. First thing, choose your county of interest. I'm going to go with Amador County. And then decide which variables you're interested in. Let's say we only want English units, so get rid of megagrams per hectares. And then you can decide whether you want all data for that entire county or whether you're only interested in biomass within a tier 1 high hazard zone or a tier 2 high hazard zone. I'll go ahead and say I only am interested in biomass in a tier 2 high hazard zone. You can either view the summary of the biomass in this county, or you can actually download the pixel by pixel data that you could use in ArcGIS or some other GIS software. If you are interested in analyzing the data, choose what file format you want that in. Otherwise, if you just want to look at the results online, ignore that step. Once you've selected all these, you hit submit. The map automatically takes you to the county you're interested in and processes. This does take several minutes. I'm not kidding with this disclaimer. There's quite a number of gigabytes powering this process, so please be patient. Know that it will eventually work. And while this is going, why don't we see if anyone has any questions so far? Let's see. I see someone asked, you said some of the data was 2012. Where is the recent data coming from? The base data comes from 2012. That's the lemma gradient nearest neighbor map. And then the aerial detection survey data is coming from 2013 through 2017. So the idea is take a snapshot of what forests look like in 2012 and then subtract out the dead biomass that is from trees that have died between 2013 and 2017. Subtract that out from the live, and that's what you get with the live biomass. And then whatever you've subtracted out based on aerial detection surveys is the dead biomass. So it's cumulative, all aerial detection survey data from 2013 to 2017. Good question. We have our results. Now you can choose to download a summary table, which shows you exactly what's up here in the upper right. But if you'd like to save it in a CSV or Excel file format, you can open it this way. The first column here is just what we call the layers on the back end, so you can kind of ignore that. The next column is the layer name as you see it on the legend on the map. We have mean values and sum. So for percent dead biomass, min and max, that just means lower bound and upper bound. You can kind of ignore the sum of percent. I don't really know how anyone would use that. If you can think of a way to use that, cool. For dead biomass, this says BDT per acre, min and max. If you look up here on the right, these values correspond to like the 148,516. That corresponds to the lower bound total, and it's in bone dry tons. Even though this says bone dry tons per acre, it's the sum once you converted it to bone dry tons total. So this is the number of bone dry tons of dead biomass that we've estimated are in this county according to the minimum lower bound. Okay, I'm gonna close out of this for now. If you do want to spatially analyze the data, you hit download results, and then the file format that pops up is what you selected when you selected your area of interest. And that'll be in a zip folder with all of the files that you need. I'm not going to talk too much about how to interpret the geospatial data that you can download. If you are interested in that kind of thing, definitely let me know, and we can incorporate that in a different help session. Now I'm going to head back to our Choose Area of Interest screen and change it up and select an area of interest by polygon. Let's say I've got the data that I want for Amador County. Great. Now what I really want to know is I want to know about dead biomass in Tier 1 high hazard zones that are near this road 88 within Amador County. I can actually draw a polygon to get at precisely that. So you hit the Draw Polygon button, and then just click on the map to create a polygon. And let's say I accidentally click over here and I don't want that. It's totally fine. Just go up here, hit the trash can. It'll clear areas that have been selected, and then start over again by hitting this button again. This isn't a very precise polygon, but it's just for demonstration. Let's say this is the polygon I want. I finish it off by double clicking, and then I can hit submit. You can choose which variables you're interested in. Let's say I want it in all the units, And for this case, I want it in Tier 1 high hazard zones. Hit submit. Again, this is going to take a second. Probably will take less time because this is a smaller polygon though. I see a question came in saying, is LiDAR data being used to refine the ADS data? That is something that is happening long term. With the Lemma Lab gradient nearest neighbor maps are being refined right now using a combination of remote sensing data and LiDAR data. And eventually I would like to update this map to include those latest, most well-validated data sources. That's a good question. One issue with LiDAR data is it's hard to use it for the entire state, whereas aerial detection survey data does exist for the vast majority of forested areas in California. Any other questions people want to chime in with? The work I got a question, who is doing that work refining with LiDAR? That is the Lemma Lab that's based out of Oregon State, Oregon State University. It's LEMMA is the name of the lab. Dave Bell is one of the people working on it. And if you're interested in that kind of stuff, I encourage you to check out a fourth climate assessment report that was written for the CEC that came out a few months ago. First author is John Battles. David Bell is another author on that report. I can actually, if you let me know, I can send you that report, and it gives some information on the latest version of the gradient nearest neighbor maps, which are being used to develop this map. Okay, so now we've gotten our results for our polygon of interest. I'm not going to download the summary table or the results table because it's going to be very similar to what we did for the county level. Last thing, downloading a shapefile, or sorry, uploading a shapefile and downloading results based on that. In order to use a shapefile, the first thing you need to do is zip up all the files that comprise the shapefile. So I'm going to go to my folder. This is a shapefile of Sequoia National Park boundaries. I'm going to right-click on this, send to compressed zip folder. So that's the first step, is you need to zip it up. Then go back to your map, choose file, select that zipped up shapefile, open it, go back and decide if you want tier 1, tier 2, or all data, hit submit. And again, this is going to take another couple minutes. You can see there is the theme. While this is processing, since we basically have already been here and seen what happens, I'm going to look at the last option, which is printing. I skipped this button here because it just takes you to that tutorial from the very beginning. I don't think we need that, but it could be useful while you're using the map to refresh your memory to go back to this info button. If you want to print what you see on the screen, hit the print button. There are two options, either layout or map only. I find layout more useful because it gives you a title and a legend and a scale, which I think are always essential for a map. So I'll show you how it works with the layout. First, give your map a title. I'm going to call this Sequoia National Park. Choose the page setup that you want. Let's say A4 landscape. Choose whether you want it to be a PDF, JPEG, etc. Advanced options allow you to set the scale. So as you zoom in and out, you can see this scale is changing. If you want to customize it for a specific scale, you just select scale. Let's say I want 400,000. I'm going to go down here. I'm going to increase the resolution, maybe 125. I do want a legend for sure. And I don't really want this purple there because that's kind of distracting. So in order to get rid of the purple, I'm going to go back to select area of interest, and our results have already popped up. So I'm going to go back to the select by drawing a polygon screen, and you can use this trash can button to clear the graphics and then go back to the print screen. And then you just hit export. This should not take that long. It's just making a screenshot essentially. And then there's your map as a title, scale, legend, etc. I'll show you the map only option real quick. It's basically just very simple. Scale is fine, hit export. So this is just a bare bones map, no title, no legend. And that brings me to the end of the tutorial. So does anyone have any questions? If you have any questions, just type them out and Stacy will help me see them and answer them.
Thanks, Carmen. So the first one we have, and so again, we have plenty of time for questions left over, is could you give some examples of what questions or projects do you expect this tool to be used to answer, and some examples of what it can't answer?
Yes, so this web map could help you understand questions that are related to feedstock availability overall for an existing or potential biomass energy facility. That's one example. So if you're interested in building a biomass energy facility and you want to know generally how much dead biomass in high hazard zones surrounds that potential project, because there are financial incentives right now to use dead biomass in high hazard zones for biomass energy right now, you could use the web map to select the areas surrounding your potential facility location and get a sense of overall how much biomass availability you can expect for feedstocks. What I wouldn't do is look at the map and pinpoint an exact location next to an exact intersection on a road where the map shows high biomass quantities and expect that you can drive to that exact location and see exactly the mortality that you see on the map.
Great, thanks. The next one coming up is, I imagine there are plans to incorporate the ADS 2018 data. Any idea when that will be available in a super cool web tool?
Yeah, now that the 2018 data is available, I definitely plan to incorporate it. It's just a question of when I can run it through the same algorithms that I use for this previous data. I would expect within the next month or so to see that. I do want to make a note about the 2017 and 2018 aerial detection survey data. They did change the protocol a bit, so that instead of recording numbers of trees from the airplanes, they record binned categories of like low, moderate, high mortality. And so the data as it's represented when I download it is just like only 5 numbers of tree densities, because those 5 numbers represent the midpoint of each bin. So the 2017 and 2018 data from aerial detection surveys are a little bit less precise than the previous aerial detection survey data, which I think is one reason why I'm excited that more advanced methods of accounting for tree mortality are coming out, like what's happening at the Lemma Lab in Oregon.
Great. So we do have a little bit more time. I'm going to take a brief pause here and talk about a few things. So as I mentioned, everybody who's registered for this, within the next week, you're going to be getting a follow-up survey from me. It will include Carmen's contact information, the PDF file of her slides from this presentation. I know she mentioned like the report. We'll make sure that link is in there if you wanted to see that. And then perhaps most importantly, the recording. And then second most importantly, I will be sending a survey. The survey is a very short evaluation. It just helps us to know if this webinar is working, if these topics are the right topics, and reports back to our funders if this is effective. And then secondly, it's going to include the option to test availability if you wanted to do a smaller group workshop on this tool with Carmen. So there's going to be some dates there. You can mark if you're available, if you're interested, kind of what kind of topics, what we need more information on. So that's going to be coming out in the next week. I also wanted to mention that if you are going to the March 14th Tree Mortality Data Network meeting in McClellan, Carmen is going to be there, and she's going to advise that if you're interested in this, to bring a laptop. And the hour after the meeting, you can sit down with her and kind of go through some of this. So with that, we're going to get back to questions. Here's a quick one just to get us started. Do you have a list of your assumptions anywhere in the data used?
Yeah, we've submitted these methods to the California Energy Commission as a technical report. And if you are interested in reading the assumptions and the methods in detail, I can send you that draft report. It's not published yet because it's still in the review process at the California Energy Commission, but just let me know and I'll send you that.
Here's a fairly specific question. Does your data cover the entire state, for example, Santa Cruz County? I can't seem to get any results which contrast with the ground truth I've observed in the forest. So is this a question of resolution or what might be happening?
I'd be curious to see what you're looking at and how it compares to the web tool. What you might be experiencing is that the aerial detection surveys do not cover every square inch of forest in California. And you can actually look online at that Tree Mortality Task Force Tree Mortality Viewer that I showed up earlier. This one, just Google Tree Mortality Viewer. And one of the options is to view where the flight paths are for the aerial detection surveys. And if there was not a flight path near Santa Cruz, then there's not going to be any data for Santa Cruz. These surveys more focus on public land. They do try to capture the majority of private land, but they don't always get to all of it. Also, one thing I would note is that the mortality surveys are specifically designed to capture tree die-off, so pockets of dead trees, as opposed to background tree mortality rates, which can increase because of climate change, but they aren't representative of the kind of episodic mortality events like what we've been seeing later. So, for example, ADS is better at capturing beetle outbreak caused mortality than it is at capturing background mortality rates. So I would be curious, I don't know a ton about the Santa Cruz area, but I'd be curious if what you're looking at is more the background mortality rates that wouldn't be captured by aerial detection surveys.
And along that note, here's kind of a follow-up question to that. So if for these aerial detection surveys, are there species or types of forests that are not well captured, like maybe in Santa Cruz or other areas?
The best captured forests are going to be the mixed conifer forests of the Sierra Nevada, because that's where we've seen the greatest concentration of die-off in the last few years because of beetle mortality. So like you can see on the web map, it's mostly this band of lower elevation mixed conifer forests, pines, firs, etc. So where there's mortality, that's where the data is the best. In areas that have lower mortality rates or maybe just background mortality rates, like Santa Cruz, you're not going to see as great of data.
Well, I'm looking through our question list, and it looks like we have answered everything. So I'm going to give one last call for questions, and if I don't see someone frantically typing out, we'll go ahead and take a break from today. So again, do look for that email within the next week of this presentation recording, survey links, and any follow-up. Looks like we're good on questions. So thank you so much, Carmen, for joining us, and looking forward to seeing how this tool is used.
Thank you, Stacy.